All right. Good evening, everyone. Thank you so much for being here tonight. And before we kickstart properly, I will just like to use few minutes to celebrate Naija Java User Group. For those that have been following us now, we all know these are months of anniversary, and while we are waiting for others to join, I will just use few minutes, 3 minutes to play a short video to showcase the journey of how far we've gone for this 365 days so far. So I'll be sharing my screen while I play that. Just a sec. So confirm you can see my screen. All right, so please listen and be, well, I say listen and be blessed now, or listen and be inspired, yeah. So thank you so much. Thank you so much, everyone. I feel so emotional right now. All right. Oh, thank you. Thank you. Thank you, Rosemary. Thank you, Samuel. Yeah, so we'll continue again. We'll be playing that video for the rest sections for the month. And let's just go into today's section without wasting much of our time. So I'm welcoming everyone to today's section. I like main talks. I'm super excited to have you all here today. And for those joining us for the first time, you're welcome. But I think all the names I'm seeing here are so familiar. Today we'll be talking on virtual trades. And I want to welcome, without wasting our time, the speaker of tonight's section. Like you can see in the video, he appeared almost like 5 times. He has been on this back to back. He'll be walking us through virtual trades today, and we can keep our questions at the end of the section. And do enjoy your section tonight. Samuel, you can have the floor. Sorry. Please let's react as we welcome Samuel. He's also the Naija Java User Group admin. It's just Rosemary and okay, thank you, Balogun. Thank you. Samuel, you can have the floor. Thank you.
Sorry, good evening, everyone. Am I audible?
Yes, we can hear you.
Okay, thank you very much. I would have loved to show my face, but I don't know, these days, pimples has been doing my face for some reason. Okay. Good evening, everyone. I'm actually very excited about this topic, virtual trade. I've been studying it for some time now, so I hope I'm able to deliver. But before I go into the topic proper, I just want a disclaimer. So we are definitely not going to be touching everything. Exactly, we are going, because there are some very complicated part that I know deserves like 1 month of study, and I've not really dabbled into that. So, but just in case I'm going through virtual trading, I feel like, oh, somewhere you missed that point. I didn't. I'm just not going to touch everywhere. So let's dive right in. It's a very interesting one, and I hope you guys find it very interesting. And we'll also do some code, not write code, there's an already existing code, just to experiment with virtual trade, because it's something you can actually simulate and see how it actually works. So without talking too much, because I like to talk too much, let's go. Okay, I think I'll need a new, just give me minutes so I can type. Just in case I want to type something. Okay, that's good. So virtual trade, why waiting became expensive and how Java made it cheap. So virtual trade is particular to Java 21. Yeah, Java 21. So it came up. So it's other languages. I've not used other languages extensively, but other languages might have their workaround. But this is one of the gifts that Java 21 came with. And for those that have not tapped into it, yes, there should be a reason why you are not using it. And for those that are using it, there should be a reason why you are using it. You shouldn't just jump on top of a new concept because it is new. You get. So let me go to the next slide. So what is virtual trade? Let me just give a brief definition, so we have something, we have an understanding as we go. We have an understanding, so I'll be able to carry us along as we move. So basically, what we'll be seeing throughout this particular slide, to get to the traditional trade or platform trade, or platform trade, and then we'll get to virtual trade, and in between you also hear OS trade. So you get to understand, okay, what those things are. And before you talk about what those things are individually, you need to understand what trade is by itself, like what trade actually is. And it's a very important thing to know, and I suggest and advise that you just take, even if it's a month-long study on trade, because your application is a giant process. First of all, let me just give us a definition of trade. Trade, they say, is the smallest unit of a process. Trade is the smallest unit of execution within a process. I don't know if we get that. I'm not seeing. Okay, I don't think I can say a reaction, but I believe we get that. So thread is the smallest unit of execution within the process. So just picture the service that you're running, or the application that you're running, as the giant process. Itself is the process. That application that you're running itself is the process. Now, thread is what actually handles individual tasks. For now, I'll just, not to be ambiguous, you get, in the statement I make. So I want to narrow down to Spring Boot application. You get, so how your Spring Boot MVC application is set up, where you have requests coming in, you get requests coming in, and then there's a thread that picks it up and handles it. You get, also another disparity, so we get to understand where I am at. There's something called connection pool. They are not, the thread we're talking about does not branch into that particular aspect. The thread we're talking about is seated in your application. It's seated within your application. It apples, so it's a slice of that process that is going on, and it's a slice that actually handles a request that come in. Now, before we go further, let me just switch to this place. And so something we might have seen before. Let me share the stuff instead. Okay. Please react if you can see the new screen I'm sharing. Can we see it?
Yes, we can. Is it a document?
Okay, good.
A doc.
Yeah, it's a document.
Okay.
So I want to confirm that you've seen this particular thing before. New. We have exec, then we have this. Have you seen this before in our application logs? How to get that reaction? We've seen it before. Okay, good. Only Rosemary. Nobody else. Okay. Okay, for those of us that have not seen it, when you run your application, pay attention to when request comes in. So it might have another name, it might have an S, or it might be, but it won't be far different from this. So this actually statement is telling you that this is an HTTP request, and NI means new input output operation, new input output. Then your ATAT stands for your ports, and then the exec one is the name of the thread that it is attached to. You see this repeatedly across your application as it runs. You see this across. So it's telling you, okay, this request is coming in, it's handled, it's coming in through port ATAT, it will be handled by exec one. That's the name of the thread. So also, I want to still give us more context into what trade itself means. Let me share this instead. Okay. Also, you can see trade as, give me a minute. Okay, you can see trade as not a cash, but trade itself is a its old context of a request. Thread itself does not carry your request. Note, thread itself does not carry your request. It old context of a task, or let's say your request. So it's old questions like, where was I, what was I doing, and what state do I need in order to continue? That's what your thread is carrying per time. So it's more like a pointer to the actual request. So when your request comes in, it is stored in a memory, it memory, and then your exec carries information about that particular request. So it's like a pointer to the state of that particular request, what is handling it, how it should be handled, and every instruction that it's needed, that particular request. So that's what your thread actually carries, the context of your request. So we are going to be looking at how many worker thread do I need, and virtual thread in question. So, and then there's the DB parts. I'm going to touch on that a bit, but in context of this thread itself that you're talking about within your process. So what we'll be covering? We'll be covering thread itself, which I just give us an insight into. Then we will talk about platform thread, talk about another important concept, blocking, I guess. And then we'll talk about the virtual thread itself. Then we'll look at the costs. You get it. It's not, like I said from the beginning, it's not every time you actually want to implement, you want to use virtual thread. It's good. I've seen how it works and makes you save a lot of time. It gets, but it's not every time. It's not for every time. In fact, when you we'll get to see when you don't really need virtual thread. Yes, and when you actually need it. I mean, it's good that you know when you need it, so you implement it, so you don't just use our expensive platform thread. And then look at sweet spots, the application itself. So, like I said earlier, a thread is a reasonable execution context. So a thread carries the information it needs to carry on, complete a request from, let's say you want to get a user information from the DB, when it comes into your application, the thread picks it up, picks context of that particular application up, and then it goes straight into your application as it is like an atomic part of the process itself, which is the application, and then carries this information. Okay, so whenever at any point a context or something is needed about that particular application, probably you supply an information. You get it, because okay, let's say you want to get a user. Let me switch here, share this stuff. So let's say you want to get user by ID, and let's say the user ID is 1, for example. So let's say what your thread does not carry that information. 1 does not carry the information. Your 1 will be stored in heap memory. So what your thread carries is reference. Thread just carries reference to that particular stuff in your memory, in the memory. So whenever it is needed, it points to that particular information, and that information will now be used in your DB. In your DB connection pool. That's another topic for another day, but it's also very interesting, as interesting as thread itself. So let me carry on. Share the story. Okay, so this is what your thread, as you can see this, where was I, what was I doing, what state do I need to continue? So these are the informations. There's the program counter, there's register counter, there's thread, there is stack, and then there's network. Now, all these things here is I think I would go ahead of myself. Is actually the disadvantage of one of the disadvantage of platform threads. You get, so I'll just give us the difference between the platform thread and virtual thread. But before that, let me just then finish this slide. So we have the CPU. The CPU is what actually executes the machine instruction using the thread current execution context. So the information the CPU needs to actually run the line of code or the instruction that is given, that has been converted from Java to machine language, is gotten from the execution context. So it's just like the thread itself carries memory for a particular request that the CPU needs to actually execute that request properly. You get? So thread is not request, and thread itself does not carry a code. You get? So because the concept of thread is actually abstract. It's just like when you are doing atom in when you are studying atom in chemistry. Yeah, it's very much abstract, but there's a context to it. There's an abstract mechanism, you get, that could make you understand thread. But the fact that it's abstract, that's what now even made it complicated, but yet you can still understand it. You get, to an extent, you get. So that's why it's still something that is still deeply studied. The right research works for this and other stuff. So let me move on. So we have the process. The process is like I said, the process is the running application. Thread executes context inside of the process. So we have the process, JVM, heap, load, class, application resource, sometimes states, and other stuff. Then you now have thread, which is like the atomic side of the process. You get, like I've said previously. So you have the thread A, thread B, thread C, thread D. And then you have your logical unit in the CPU that executes and does scheduling. Before your there are lots of, if you've done, okay, there's this very complicated topic when I was an undergrad, operating system, very complicated. One of the prevalent thing you see across is, sorry, give me a minute. Sorry guys, okay, so one of the most prevalent discourse around operating system is queues, scheduling, blocking, state blocking, and all those stuff. You get, and before your thread gets to the CPU, because your thread does not really enter your CPU, it just supplies information for the CPU. So before your thread gets there are lots of scheduling and there are lots of queuing. There's the queuing before the request even gets to the thread, and then there's the queuing before the thread is before the context of the thread is handed over to the CPU for the CPU to be able to operate. And then there are lots of scheduling in between. There are lots of scheduling. There are different scheduling mechanisms, but we are not going to talk about that today. So next, then we have okay, waiting is not one thing. You get, in Java, blocked specifically means waiting to acquire a monitor. Now, okay, I don't want to talk more on this because it will deviate us from understanding the importance of platform thread and then the virtual thread. But let me just give us an overview, just surface. So we have the runnable. These are different states that a thread can be. You get, these are different states that a thread can be. We have the runnable, we have the blocked, we have the waiting, we have the timed waiting. So in the runnable is like, I'm ready to run. You can use me. I'm ready to run. You can use me now. I'm available. Blocked in the sense that can be waiting for something. I'm waiting for monitor. And monitor in a sense, let me just give us a brief on monitor, because monitor is a word that comprises of several things inside of it, which is monitor contains it's telling you that it contains notify, it contains a lock, and lock is a lock is like a state where a resource is held by another, by a resource is held by process or a thread. Yeah, a resource is held, so that particular state is called locked, and it implements a mechanism called mutually exclusive. So as long as I'm holding this, you are excluded from touching it. So it's a lock. So the monitor itself comprises of that concept and also the notify concept and then the scheduling. So you are scheduled and then you are also notified that okay, this particular resource now is available, you can pick it up. You get that the monitor is actually broad concept. Don't just take it by its words. It's deeper than the monitor just there. So we have waiting. Waiting is different from block. Waiting, something can be waiting indefinitely. You get something can be waiting indefinitely, probably for another thread. You get probably for another resource or for another process to do something for it, or it can be waiting for DB to return something to it, or it can be waiting for another service. You get, if you are working with microservice, can be waiting for another service to deliver something to it. You get, so waiting indefinitely. That's why you as a programmer, you have to implement timeout and other stuff. Then, so blocked is mostly I would say within your OS scheduling. You get, why waiting can be not predictable. You get, so then there's the timed waiting. There's the timed waiting where you don't wait indefinitely. You actually set a timeout. You get, where okay, once this is not, just carry on. No, once this is not done yet, okay, just through an exception. Don't. Yeah. So you time even with a terminal state in mind that you are going to terminate even if this is not done. You get, so let's talk about platform thread now. So platform thread and OS native thread, I think the best way to think of them is point of views. Like you are talking about the same thing but from different point of view. I hope you are following. So when you are talking of platform thread and your OS thread, especially when we are dealing with Java, again, you are talking of the same thing but from different point of view. So when you call a thread a platform thread, you are coming from the Java. Coming from the Java point of view, so you can be talking about how JVM relates with it and stuff. That's Java version machine and stuff. But when you're talking about the operating system, there you'll be talking closely to how the CPU handles it and other stuff. But the reason that makes it actually the same is the fact that the under the hood of your platform thread is the OS thread. So that's why they are not different. You get, under the hood of your platform thread is your OS thread, the operating system thread. You get, so that's why they're really, in fact, there's no way they talk about it that they're actually different, because the platform thread is literally your OS thread, your operating system thread under the hood. And why does this really actually matters? Let's go. Now, the Java platform thread is same as the OS thread, and then there's the scheduler, there's the logic CPU, there's the native stack, there's the kernel bookkeeping, then there's root counts. Now, why does this concept really matters? Now, if you build your normal Spring Boot MVC, your Spring application, no virtual thread, nothing. Now, platform thread is expensive. Now, platform thread is expensive in the sense that I will see that practically. I'll show us the results of what I mean. I'll give us, we'll see 4 results to show us what that actually means when we are talking of it's expensive. Now, it's expensive in the sense of the resources that it actually uses. You get, it's a real thing. You get, your CPU, it uses real things. Your CPU, it uses it uses those resources that are, let's say, encoded to to your CPU. You get it uses the counts, it uses the native stack of your application, of your system, your operating system in general. It uses, so it's not really managed by the Java virtual machine itself. You get, it's not really, it's managed by your operating system. So it carries the weight of what your system provides. So it's not something that you can just come up and write a code to actually manipulate or reduce the size. It's going to use what your application provides for it. You get, and those particular stuff are actually expensive. Imagine, although you can have lots of numbers of threads, but they still narrow down to like I have this system I'm using as it's called itself Pi5. I thought Pi5 means the number of cores, like CPU cores that are, but it's not. You can go to your task manager to see that my system uses as 10 physical cores, but 12 logic cores. I don't know how it does that. It's not, because when I was doing my research, it varies. It has 10 cores, but 12 physical cores. So it is from these cores now, your threads are actually a byproduct of these numbers of cores that you have. You get, so because they are closely related to the core of your system, that makes them expensive, because you can barely control their size. You can, it's based on what your CPU provides, and your system provides some expensive things. You get, so when you are using those traditional cores, your system will definitely eat up. You get, because you are using things that are definitely close to the system. So I hope I think there's still more, but that's one way to communicate how expensive using platform thread is actually. You get, so when you're using your when you're running your Spring Boot application, that's what you're using without the virtual thread. And okay, let's move on. So this is the concept now. The traditional your platform thread, the traditional MVC that uses the normal thread, the sample that I just gave us is traditional. Request came in, use my platform thread, which is still closed, which is still the same as my OS thread. Now the thread comes in here. Now the thread, that particular request needs a DB response. Probably wants to, like the example I gave in that sheet, needs a DB response. You will have to wait for the DB to respond and then give it. That's why if you look at, let me share this screen again. Share this tab. Now, if you look at your logs whenever you are running an application, you see something like this. For those of us that said we've seen, you see something like this. For one same request, you see something like this, something like this. You have those other gibberish. I'm just repeating this. See something like this. Then later, and in between this, you can see something like this also. You can see 4. Thread 4 is also doing it, because they're working in parallel. That's why you see something like this. But eventually, when thread 1 is done with what it is doing, it will pick up another task. Which is not that request, that came in. That's why it is very advisable that you use something else to differentiate processes when they are running on your logs, because you can search by this on your logs and you get other requests or other tasks under that particular stuff if you are searching by this on your logs. You get, so, but within this now, there can be a DB. That particular request can want something from the DB. So it can want something from DB, and it will make this your thread to wait. It will cause this to wait. You get, it will cause this particular native thread to wait. So you are causing something very expensive to wait for DB instead of to wait for a DB response, or maybe another service, something from another third third party. It's waiting for something third party. Then it waits again. You get. So that's the particular point that that's where virtual trade actually comes in. And it will amaze us how virtual trade actually solves it. You get. Virtual trade, okay, let me not go ahead of myself. Share this instead. So you can see now, request comes in, there's split from thread 1, DB waits, or something else, another process that makes it wait. It waits, gets the request before proceeding. Same thing with platform 3. Now, these things, they are operating in parallels. You get, they're operating in parallels. Now, you can check your task manager. You can check your task manager. You see that your application gives you a lot of threads, produces a lot of threads. Take in mind, when I checked, I saw 6,000 or 60,000 threads. You get, so that's like you will think, or not think, I mean, actually your application is running fast. You get, because you have lots of threads that are attending to the many requests that are coming up. And even without anything much, you can do more for horizontal scaling to actually handle even more requests without even virtual thread present. But virtual thread helps us when we get to virtual thread. Sorry. Okay. I hope we get these points. I don't know if we're together. Let me check my screen. Are we together? Hello. React if you are still with me. I'm kind of boring. Okay, thank you very much. Okay. Let's go. So concurrency is achieved by having many platform worker thread. You get, you need to have like lots of platform thread working. You need to have that's what makes concurrency achievable in traditional MVC. Now, let's go to, I think, okay, let's go to virtual thread now. The beauty of virtual thread, the beauty of virtual thread. Now, virtual thread, you know, this previous slide I showed you some of the things that your traditional thread uses, like, because they also use memory. So the place that they store your memory and all the stuff, they are using I would say your native resources. You get, that are way expensive than something that is abstractly managed by your JVM, Java Virtual Machine. Now, for virtual thread is as the name implies, virtual, but it's a thread, but it's virtual in the sense that it is managed by JVM and Java Virtual Machine. You get, so I believe that's where the virtual is actually coined for. You get, it is virtual, so it is managed by JVM. So it does not really use this directly now. So because definitely you need an hard drive. You get, definitely you need those things that are native, but it does not directly. It itself does not directly go there to use those heavy resources. So what it does is what lazily that makes it faster. It does its work lazily in the sense that it latches itself onto platform thread. So all those things now will be handled by platform thread, while the virtual thread itself does not really carry much. Again, that's what made it a core virtual thread light. Yet virtual thread is actually light. And the reason is that it's not doing the heavy lifting, is done by the carrier. They call those platform thread that carries the virtual thread, they call it a carrier. You get, so for virtual thread now, just like a request coming, just like we have a request coming now, imagine it comes in and the virtual thread takes that particular request and then latch itself onto a virtual platform thread. You get, latches itself onto a platform thread to carry it, and now the platform thread carry it and does the heavy lifting. Now this is where it now gets interesting. Is that, you know, previously in this our previous slide, when the request comes here, the platform thread itself carry it and then waits for DB for something. Let's say you want to get a particular user information. But for virtual thread, now there are two things not working. It has the virtual thread is like the one that holds the context for that particular task. Now it latches itself onto a carrier thread, which is a platform thread. It latches itself there. Now the platform thread, once it gets to a point where it waits for something, probably waits for a DB, probably waits for a request, it detaches itself. We call this the name of that is called pack. It packs the virtual thread packs so that the virtual thread, the platform thread can go and do something else. I don't know if you get what I just explained. So previously, our expensive platform thread would wait for a particular task for a particular DB request or another third party API request. But this time around, instead of the platform thread to wait, the virtual thread will be the one to stand to wait and allow the platform thread to do other things. So what you now have is that your platform thread, instead of waiting, it can now go and do all that. So what you have, you can see these bubble stuffs. You have lots of virtual threads. You can have lots of them because they are virtual, they are managed by JVA, and they are very light. You can have lots of them. So lots of them can be, let's say you have 100, can be picking different requests and then latch themselves onto a platform thread where they get to the point where they are supposed to wait for a request. They tell the platform thread, go and do something else. I'll wait here not for you, because another carrier thread can take them up. So they have the JVM has a scheduler. It uses to schedule virtual thread. So once it gets to that wait period for anything, the virtual thread just detach itself. The concept is pack, and it packs so the platform thread can go and do other requests. So imagine how many things you can undo, you can process at that particular time. Now we'll come to, let me just go. I don't want to move ahead of myself. Okay. Now this is the art of a virtual thread visually. So we'll see what it does. So the virtual thread, a request comes in, it mounts on the carrier thread as you can see on this slide. Then when it comes to wait, let's say for database is not ready, the virtual thread packs it unmounts from that carrier that it's using, and then the carrier runs another virtual. The carrier goes for another virtual thread. Now, like I said, you have lots of virtual threads because they are lights managed by JVA. You can pick requests and other stuff. So another virtual thread, it goes and carry another virtual thread. Now, let's say this particular one that you have here, this particular DB now is now ready. So what now happens? The Java Virtual Machine scheduler schedule that particular virtual thread for another platform, for another carrier to carry it. So you get more work done, because the platform thread is actually the most important thing, because the one that actually relates with the CPU, not your virtual thread. You get so it gives room for your platform thread to do lots more things. Yeah, it's just like it buys time for virtual thread, for platform thread. That's literally what virtual thread. It is light and it buys time for platform thread to do more things. You get so virtual threads are also blocking. If there's this, you can mistake that NIU from this particular. Let me share this stuff. Oh, time is already gone, and I want to show us this. You can mistake this NIU. This it's actually new. Let me spell it out. NIU stands for new input output. But you can probably read an article or even doing your research, and you stumble upon something called non-blocking thread. Non-blocking thread is a myth. It's not real. There's nothing like non-blocking thread. It's a myth. It's a myth. Now I stand to be corrected, but note again, I said I'm not going to be touching certain things. So I'm not touching NetC, Webflux, and all those stuff, reactive programming. No, I'm not talking about them. On this particular concept, non-blocking thread is a myth. And I'm sure even when you get to that particular concept, it's also a myth there. But I've not really delve into that web flux and reactive programming. I get. But the reason why I say so is that it is not the thread itself by nature does not have the ability to say it doesn't have a feature to be non-blocking. It's like a string, a rope. It continues. It does not have a feature to disappear here and then reappear somewhere. No, it's like a straight. It works in a straight line. Then something happens, it will bend and take the other route. So probably it's that feature of it bending and taking another route that makes that non-blocking concept comes about. Because as you can see in the previous slide, you can see that the virtual thread actually waits. It doesn't switches. It doesn't become non-blocking, disappear and reappear. No, it actually waits. Then allows the platform thread to carry on and do other tasks. Now that concept might make you think that it is non-blocking. It's actually so what makes non-blocking is the operation itself. Like a DB call itself is blocking. So what is that particular where it exists in the task execution, again, that makes it non-blocking, not the thread itself. So when it's in the face of DB and as long as you do not implement reactive DB or stuff, it will be blocked. So let me just go further. So they are designed to make blocking style concurrent. So virtual thread are to make blocking style concurrent cheap and not to turn blocking code into non-blocking. You get they make it cheap. So there's nothing like thread switching. That's scheduling and CPU switching between execution. So the virtual thread are light, they are not free. Virtual thread are light, they are not free. So let's look at the costs. Oh, I only have 10 minutes. Okay, so let's look at the costs. Virtual thread, JVM scheduler. You get JVM, they are light, yes, but they come with a cost. They come with a cost. There's the JVM scheduler, there's the carrier thread. Previously in this slide, you have just one request, one thread, and then wait for but for the next one, we now have 2 threads for just one request. So we have our platform thread, and then we have virtual thread attaching itself to carrier thread. So we have another carrier thread, then we have the OS scheduler, then we have so it adds that complexity. But the good news is that it is depending on the application that you are or the system that you are building, it is mostly the cost is bearable. Yeah, the cost is actually bearable because it's handled by Java virtual machine. That's the abstraction of Java itself. One of the beauty of Java, you get. So we have 50,000 concurrent blocking tasks. The purpose is about resource representation, not magical stuff. So the virtual thread itself does not make your CPU good or less better. It does not add anything to your CPU. In fact, what it does is that it gives your CPU more tasks to work with. It gives your CPU more tasks. So there are times where your CPU actually waits. When you are using, let's say when you are using traditional platform thread, there are times where your CPU is actually waiting because one of those threads they are waiting. One of those threads or a couple of those threads they are waiting for DB to actually release resource or something else to release resource. You get. So your CPU is probably idle. But now your virtual thread is such that platform thread will not be idle. You will not be idle. Instead of the platform thread to wait, don't wait. Go and pick something else and give to CPU. Don't wait. Go and give the CPU. So it gives what it does is that it gives CPU more work to do. And let me not say more. Based on how you build the system, if it's actually not required, you are definitely giving your CPU more work to do. But if you build it based on your system has those lots of traditional Spring Boot, you have a DB call to make, you have another service to return back to you, return information. So there are lots of weights within your Spring Boot application. That's what makes virtual trade actually profitable. Because once those things exist, now virtual trade comes in. That's where virtual trade actually wins. So once they exist, okay, CPU would be having, because if there are lots of weights, CPU will have a lot of time to be idle. But with virtual trade, it gives your CPU enough work. So there's no time your CPU is resting, your CPU is always working. You get? So they do not create more CPU, like I said. They don't add them. They just give your CPU enough work. You get? They give your CPU enough work. If you don't need it, if there is no wait, in fact, if the application does not have anything to wait for, if it's just, let's say, application that just display or does not really have anything to do with DB, or is not DB intensive, it gets, or, and maybe even, let's just even boil it down to a method level, that the method you are calling, or the method or that particular implementation that you're doing does not really have anything to do with DB, so it doesn't really wait much. Not only DB now, because I've been using DB, there are other reasons that can make your application wait. It can be calling a service, waiting for a request for something or something. If your application, if that particular service you are bidding, because I know we mostly implement this on the method level, again, if that particular method does not have lots of weight, you really do not need virtual trade. It's even expensive at that particular point. So high concurrency plus significant weight plus block, that is where virtual trade actually shines. Let me just skip through, because I'd like to show the code. So virtual trade don't create more CPU. It doesn't. It lets you waste fewer expensive thread while waiting for everything else. You get? No, the first explanation is that instead of your platform to be to be waiting for a DB or something else, he said, no, don't wait. Go and do something else. You get? And then that gives more task to your CPU instead of your CPU to waiting. You get? Let me just go to the code. So you can see what I've been straighten about. Okay. Are we together? I don't know. If we are together, please let's start. Okay. Everybody, thank you. Let me see. How do I share my screen? Let me stop sharing. Stop sharing. Share again. Windows. Okay. Share this. Okay. Can you see my screen? Can you see my Visual Studio code? Can you see my Visual Studio code? Okay, thank you. Thank you. So, I just saw this. I like, oh God. Okay, let me just go straight to the point. Just like writing method, so does one thing. So now we have our main method here. I'm not writing a code, it's already written. So we have our main method here. This is what execute run. This runs our platform thread, and this also runs our virtual thread. So we have those two threads, and then we have this the method. I think the only special thing here is this new fixed thread for platform, and the only special thing here is this. Nothing else is special here. So what else? So submitters, this the method is right. So we have the simulator now. The simulator is what's now the simulator, what it does is it simulates requests and also give us a feel of weight, like when you are waiting for DB, when you are waiting for image to process, database query, HTTP client send, you are waiting for a third party or file read and other stuff. But mostly the virtual thread implementation is mostly important, mostly shines for these two, not for image and not for file. It's mostly shines for database and calling, let's say, third party. So we simulate that by using this sleep. We simulate that wait by using sleep. So I'll run this application first, implementing this. So we'll see the time gap. So you know when to use it. You see the time gap between. Just let me see. Okay. Let me include this. So now these are virtual tests. These are the results. It completes within 100 same task. It completes within 1447 seconds. Now let's check our platform thread. Our platform thread used 5,123 seconds, 128 seconds. Now note, we simulated a request and we simulated a wait, like a wait, so it's waiting for something. And you know, our virtual thread makes the platform, instead of the platform thread to be waiting, it gives the platform thread free space for it to do whatever it is it wants. And it's also give more tasks to our CPU, and it is also light. Note it, and it is also light. Now let me show us something. This is the time. Now let me remove. Now you see the time gap. Let me just point this out now. You see the time gap between the two. There's like this like almost 4,000 milliseconds gap. Almost 4,000 milliseconds gap. Now let me remove the wait, so you know when you need to implement it and when you don't. Let me remove the wait. So I'll comment this whole thing out. Okay, let me run it. Let me run this. So you see the time difference between them. Now I remove the sleep period, the wait period. So we have 305 milliseconds for our virtual thread. Now check the gap between that, and the platform thread is even faster. Can you see the magic? The platform thread is even faster. Why? Because that wait. So if the application does not have that wait, you don't need virtual thread. You get? If it does not wait for anything, you don't need virtual thread. You get? So this is exactly 9:30. This is the shortest way you get to understand. Yeah. So any questions? Let me not take too much of our time. Any questions? Thank you, Rose. Any question? Maybe you can ask.
Sorry. Please hold on. Before you go ahead, please can we appreciate the speaker? It was just Rosemary that was reacting. And it's still Rosemary and Ebube. Thank you, Gbenga. All right, so everybody can mute and go ahead. Thank you.
All right, first of all, thank you so much, Samuel, for this session. I think you really did justice to this topic. Like the small confusion I had, like you have clarified it. Well, I don't know if you covered this, so because my network kept throwing me off at certain periods. But I was expecting you to talk about pinning in virtual trades, because that's like another major limitation that they have, like pinning, a situation whereby the virtual trade refuses to unmount from the underlying platform trade. So that platform trade cannot go on and like execute other virtual trades. So I don't know if you cover that.
Okay, thank you very much. So let me get this straight now. So you are saying there's like a concept, probably that's a bug, where the virtual thread itself refuses to unmount from a carrier.
Yes, it's called pinning.
Oh, pinning. Uh I didn't study that bug. I don't know that. In fact, if that exists, that destroys the whole purpose. Like for the fact I'm sure that would be a bug. That should be a bug because the concept of virtual trade is that it gives platform a carrier to. So I didn't cover that because I didn't get to that particular aspect in my research. But I believe if that exists, that's actually a bug. That's actually a problem. Yeah,
Well,
that's probably a disadvantage.
well, I'll say yes and no on it being a bug because I think virtual trade became very stable in Java 21, and pinning has two main occasions. The first occasion is when the thing happens in synchronized blocks. That is when you're trying to synchronize two trades and you're using virtual trades, and that's when the first pinning happened. That one is a bug. I think what happened was that because of how like they usually release all these jobs and specifications for the JVM was that you know they don't usually release every single thing in a particular JDK release. You get like Valhalla now will span multiple JDK releases, not just in Java 27. So I think when they released, when they became stable in Java 27, it was not fully completed. So pinning was still there. But if I'm not mistaken, in Java 25, it no longer happens in that is for synchronized blocks. You get, but the second location has not been resolved, and I don't think it's ever will because of the whole backward compatibility nature of Java. The second instance where pinning happens is um, when you're using GNI, that is Java native interface to make foreign function calls or to like call C code, you get native machine code. So that one because the JDK doesn't really have control over that area, over that C code. The thing just, if you're using a virtual thread for that one, it should just hold on to that platform thread until the thing finishes executing. You get, or maybe some older drivers that haven't accounted for that and are using C code underneath too. So I think I just want to state here so people also know. So if you are making any native, you're calling any native C code using GNI, you expect spinning to happen. And if you're not on Java 25 and you are using Java normal synchronized blocks instead of like atomics to synchronize V threads, you also experience that. So I just wanted to add. Thank you once more for the presentation. I learned a lot personally.
Wow, wow. Thank you very much for that. I mean, that was actually a worthy dev. I think I'll delve into that thing because if that could occur, if that in fact what's the percentage of that occurring? And if that could be if that would be common, that defeats the whole benefits of actually because we just see that we just saw when I ran the application that if there is no wait process, the JVM implementation you're just wasting your time because even the platform because the virtual thread adds more weight to the processing. You get so, but if there's a wait, then now imagine the virtual machine refuses to allow the platform thread go. That's a worthy delve. And thank you very much for pointing that out. I'll definitely study that and look at the percentage rate at which it happens so we know when not to implement it. So that you don't go in your code and expect it to be fast because you implement virtual and then actually something is actually happened behind the scene. So thank you very much once again.
All right, do we have any other question? Okay, so in the absence of any other question, I would still want to apologize for exceeding the time frame for the section tonight. We'll meet again next week, Tuesday, same time and same venue. Do enjoy the rest of your night. Thank you everyone for joining.